So, with Delta Lake, we are able to fill in critical layer of the modern Lakehouse architecture, bringing structure and reliability to your data lakes in support of any downstream data use case. But from a performance perspective, indexing alone isn't enough. For many analytic workloads that involve small queries that need to be executed very fast, you need more. You want a high-performance query engine that can deliver the performance required for traditional analytic workloads. I'm pleased to announce that at Databricks, we've been working on a solution that we're calling Delta Engine. So I want to welcome on stage Reynold Xin, co-founder and chief architect of Databricks, and he's going to tell us what Delta Engine looks like under the hood.
Thank you, Ali. I'm really excited to be talking to you today about Delta Engine, a high-performance query engine for Delta Lakes. Delta Engine builds on Apache Spark 3.0 and is fully compatible with Spark's APIs. This includes Spark SQL APIs, Spark's data frame APIs, and by extension, the Koala's data frames API. It delivers massive performance for SQL and data frame workloads with three important components. The first component is an improved query optimizer. The second component is a native vectorized execution engine that's written from scratch in C++ for maximum performance. And the third component is a caching layer that sits between the execution engine and cloud object storage for faster I/O throughput. Delta Engine's improved query optimizer extends Spark's cost-based optimizer as well as Spark's adaptive query execution optimizer with more advanced statistics. And this technique can actually deliver up to 18 times performance increase for star schema workloads. Delta Engine's caching layer, again, sits between the execution engine and cloud object storage where we build our data lakes, and it can automatically choose what input data to cache for the user. And it's not just a dump bytes cache that caches the raw data. It transcodes data into a more CPU-efficient format that is faster to decode for query processing later. And with this, we can fully leverage the throughput of the local NVMe SSDs in a lot of the cloud virtual machines these days. And this delivers up to 5 times scan performance increase for virtually all workloads. For the rest of the talk, I want to focus on the native execution engine and walk you through some of our thought exercises in designing and implementing this engine. Every time when we design a piece of software for performance, it's important to look at two aspects. The first aspect is what are the hardware trends? How are hardware changing and where will hardware go in the future? And that's important because ultimately the piece of software we write will run on some piece of hardware. The second aspect are the workloads. What are the characteristics of the workloads that we need to run for or on? And this is extremely important because without knowing that, we don't know what we're optimizing for. So let's first take a look at hardware. For some of you that were here 5 years ago in Spark Summit 2015, you might remember a Keynote slide in which I compared the hardware spec from 2010s compared with the 2015. And I did that along 3 dimensions: storage, network, and CPU. And we found that along the dimension of storage and network, which are basically I/O throughput, the I/O throughput has gone up by an order of magnitude in those 5 years. So it's gone up by 10x, whereas CPU clock frequency had largely remained the same at around 3 gigahertz. So as I/Os are becoming faster and faster, more and more bottlenecks are happening on the CPUs. So in response to that, we launched Project Tungsten in Apache Spark, which is aimed at substantially speeding up execution by optimizing for CPU efficiency. It's been 5 years since 2015. Let's take a look at what has changed with hardware in the last 5 years. Interestingly, I/O throughput has continued to go up. As a matter of fact, it went up by another 10x. These days, it's really not difficult for any of us with the swipe of a credit card to launch a new virtual machine in any of the public cloud providers' infrastructure. They can give you 16 gigabytes of an NVMe SSD and with a 100 gigabit network. But CPU clock frequency remained the same at around 3 gigahertz. So as every other dimension is becoming faster and faster, the CPU become more of the bottleneck, even after 5 more years. And the first important question we ask ourselves in designing the execution engine for Delta Engine is, how do we achieve the next level of performance, given CPUs continue to be the bottleneck? Now, the second aspect, workloads. In the past few years, it's becoming more and more obvious that businesses are moving faster and faster. As a result, data teams are given less and less time in properly modeling and preparing their data. If your business context is changing every 6 months or every year and you're given sort of new business problems to solve, there's really no point spending 6 months to a year modeling your data, like how you would do it back in the 90s or 2000 era of data warehouses. As a matter of fact, these days, most columns don't have sort of constraints defined. Strings are used everywhere because strings are so easy to manipulate. And many of the columns, for example, such as date or timestamp, are just stored as strings these days. And unfortunately, a lot of this characteristics of the new workloads and the new lack of data modeling are not really benefiting the performance of the query execution, because many of the query engines are designed in an era in which data are very well modeled. And we have all learned, hey, in order to actually achieve better performance, let's model the data better. So the second important question we ask ourselves in designing the new execution engine is, can we actually get both agility and performance? Can we get great performance for very well modeled data, but also still pretty good or great performance for not so well modeled data? And Photon is actually an answer to those two questions. It is a new execution engine for Delta Engine designed to accelerate Spark SQL workloads. It is built from scratch in C++, so we can get maximum control of how the underlying hardware would behave in order to extract the maximum performance. And we really leverage two very important principles. The first is called vectorization. And the idea here is to exploit data level parallelism and instruction level parallelism for performance. And the second is we didn't want to just design something that would work very well for model data. And we spent a lot of time thinking about and so making it happen to optimize for not so well modeled data. Before I explain to you how Photon works, it's important for me to give you a refresher of how modern CPUs work. So we consider it a CPU 101. While we found out from some earlier slides that CPU clock frequencies are not getting higher, there are some dimensions of the CPUs that are improving, and they mostly are around the degree of parallelism. And the first is data level parallelism, and the second is instruction level parallelism. For data level parallelism, you might have heard of the term SIMD. And what SIMD does is, through a single instruction, now the CPU is capable of processing multiple data points at once. And that degree of parallelism is measured by what we call a SIMD register width. When the concept of SIMD first came out with MMX and SSC instructions in the 90s, a SIMD register width is 128 bits. And what 128 bits register width mean is that a single instruction is capable, for example, processing 4 32-bit integers. And when the AVX2 came out, the SIMD register bandwidth actually doubled. And AVX512 came out, which is the most recent SIMD instruction set. The register width double again. So the degree of parallelism for data level parallelism through SIMD instructions has been doubling. And the second part is instruction level parallelism. What that means is when the CPU receives instructions to execute, it doesn't actually execute them in the order when they come in, or in any sequential order. As a matter of fact, the CPU will look ahead in this what we call out of order window, which is the number of instructions the CPU can look ahead for. And it will figure out, for example, can the CPU automatically reorder the instructions and sometimes run multiple instructions in parallel if they don't have dependency. And sometimes even running it in parallel with dependency speculatively in order to actually increase the throughput and performance of the software. And as you can see on the slides, in the past few years, with the newer generation of the Intel CPUs like Sandy Bridge, Haswell, Skylake, the out-of-order window has also been increasing. And about 15 years ago, there's actually a seminal paper published in CIDR conference, which is one of the most prestigious database conferences called MongoDB X100. And it's written by Professor Peter Bonds out of this institution called CWI in the Netherlands. And this paper really is the classic paper that details how we can exploit the maximum performance with the technique of vectorization that focuses on getting data level parallelism and instruction level parallelism. So for the past 2.5 years, the Databricks engineering team have been working very closely with Professor Peter Barnes in designing what a new vectorized execution engine would look like in the 2020s with all of this new workload characteristics. So first, I want to sort of walk you through some of the techniques we've used in Photon in order to exploit performance, and start with data level parallelism. The first step in designing a vectorized execution engine to exploit performance is to think about the in-memory data format. Most naturally, humans think about data in a row-oriented format. That is the first row, and then there's stative values in them. But in order for vectorization to work really well, we would transpose a row-oriented format into a column-oriented format, in which case all the values for the column, for the same column, are laid out together consecutively, and as shown on the screen here. And one of the nice benefits of this sort of column-oriented in-memory format is when we actually do any type of compute. For example, in this case, I'm just showing you how to sum up the value of two columns. We could write a very simple tight loop here, just loop over the data and to generate a new column. And if you look at this very simple snippet of code, which actually mirrors what the real code would look like in a query engine, it's very compact, and it accesses memory in exactly sequential order because it's a column-oriented format. If the data is laid out in memory using a row-oriented format, then every time when we go from one row to another, when I sort of increments, we would have to skip a column 2, which is the list of string. And that will actually lead to worse cache behavior and worse prefetching. And the other benefit is with such a simple code snippet, what we call sort of a kernel, it's very easier for the modern compilers to be optimizing such simple loops. And you apply techniques such as loop unrolling. It's also, in most cases, the compilers can recognize this pattern and generate CMD instructions automatically for us. To demonstrate to you what that means for the CMD instructions, I compiled this snippet of code using sort of two different compilers, one without CMD and one with CMD. The version without CMD you can actually see it's pretty short. And then kind of the body of the loop, I've color-coded it to show you the body of the loop. And you don't have to understand all the actual instructions being generated by the compiler. But you can probably tell in the CMD instruction, while it's significantly longer, mostly because of loop unrolling, the instructions started mostly with the verb V, right? V. And V here basically means vectorized. It means for each one of those instructions, they are effectively processing 4 or sometimes 8 or even 16 values at once, rather than compared with the left side, they're just processing one value at once. And the performance difference of the CMD to leverage this kind of data level parallelism is actually massive. With a fully CMD code, measured even end-to-end, so with a lot of overhead of sort of the system setup and all that, this sort of simple add arithmetics could generate 4 times speed up. So now we can process almost 8 billion rows per second just on a single core. Whereas the non-CMD version can only process, even though it's also native C++ code, can only process 2 billion. Now, data level parallelism, CMD. I want to move on now to instruction level parallelism. In order to explain that, I need to sort of bring up a slightly more complicated example, hash tables. Hash tables are one of the most important data structures in memory for data processing. It is used very frequently in aggregates. It's used very frequently in joins. Here, I'm just showing you a very simple example, as a matter of fact, overly simplified, that computes the sum for some values grouped by certain key. And the way this would work, so very naturally, if I were to ask you to just write this code, you probably write something similar to what I have on the screen. What you would do is you would create a hash table, and then you would loop over the sort of your input data, and for each of the row, you would compute a hash bucket, and you would do a probe to look at whether the hash bucket key is the same as the current row's key, and if they are the same, you would sort of aggregate the data value into the hash table itself. So the hash table is storing a bunch of partial sums. And to simplify the code snippet, I don't even deal with key collision here. Now, if you look at this code, it turned out most of the time are actually spent in the highlighted green part, HT bucket. And the reason is the nature of the hash table means whenever you sort of scan through some data, you're going to trigger a lot of random memory loads. That is, the buckets are just random in different random locations. And random memory loads are actually very expensive for modern CPUs to do, because modern CPUs are really optimized for sort of sequential fetches, even for in-memory data. Because CPUs run so fast, if you have the CPU have to wait for some data to arrive in a random location in memory, that wait is significantly longer than sort of just doing, for example, arithmetics. When we profiled this, we actually found that about 2/3, so 2/3 of the time for this code snippet, the CPUs are just waiting for memory, for data to arrive from memory. And the CPU is really spending only 1/3 of the time doing useful work. So the question now is, how do we optimize this code? In order to optimize it, we kind of need to know what's wrong with it from a performance point of view. And I've color-coded it, so the different parts of the inner loop for you. And then we soon realize it's very obvious that there's a lot of different concerns done in a single loop. We are computing hash code, we're doing key comparison, we're doing some memory lookups to load data from memory, and we're also doing sort of additions or aggregates. And when there's actually a very large loop body, it makes it, this actually becomes a very unfriendly behavior for the modern CPUs. And the reason is, remember what I brought up earlier, the CPUs has instruction level parallelism, has a concept out of order window, which is roughly around 200 instructions the CPU can look ahead to reorder or run in parallel. If the body of the loop is very, very long, the CPU could probably only look ahead either 1 or 2 loop iterations, which means at the maximum, the CPU can actually only reorder 1 or 2 loop iterations and sort of run 2 of those, the most expensive parts of the computation, which is the access load, do a memory load at once. So only 1 or 2. So then, understanding that, now we might have a sort of a pretty simple solution to this problem. How do we make this snippet of code fast? Even though this was a little bit unintuitive, the way to make this loop fast is to break one single fat loop into multiple small loops. It's intuitive because we are now with multiple smaller loops, we are actually running through the loop multiple times. It seems like more overhead, for example, just incrementing I. But the reason this is actually significantly better is the most expensive part right now, the green part, is its own loop. And the body of the loop is extremely simple. And with such a simple loop, the CPU can actually, in its out of order window, can predict and look at many, many loop bodies. And as a result, the CPU can see, hey, I will need to fetch from, for example, this 12 different memory locations. And it can launch all 12 memory fetches in parallel. Instead of waiting for one to complete and launch another one, it can actually launch all of them in parallel and do all the fetches at once. And this actually substantially speed up the actual computation time of this code snippet. As a matter of fact, with these techniques, plus a number of other things, such as minimizing TLB misses with huge pages, we managed to significantly speed up this core sort of aggregation functions performance in the Photon engine. And the amount of actually wasted memory stalls have also significantly reduced. So we talked about data level parallelism, instruction level parallelism. But how does it all look if we put it all together to run through sort of traditional SQL queries? And we ran an experiment just with Photon on and Photon off, and the rest is just the Delta engine. So it already includes a lot of the great query optimization improvements that provides often some order of magnitude speedups. And we can see we actually achieved a 3.3 times speedup just at the physical execution in the engine layer with the Photon engine. So far we have talked about the techniques of vectorization. It's not necessarily a new technique. As a matter of fact, a lot of other databases leverage it. Now, one thing is sort of very different, and is we spend probably more time optimizing for the modern hardware. But the other aspect is we have spent a lot of time thinking about how we can actually optimize for the more modern workloads in which people want to move faster and don't have to always properly modeled data. I won't have time to actually go into all of it, all of the tricks and techniques that we have leveraged to make string go faster, but I want to give you one example so you can understand the flavor of it. When we first rewrote a set of string functions from sort of some code that runs on the JVM to native C++ code, we observed quite a bit of speed up. For example, the upper function, we achieved almost a 50% speed up, and the substring function was almost a 3 times speed up. But we didn't stop there. We asked ourselves, hey, can we do better? Now, I have to introduce you to sort of how strings are encoded in order to understand one important technique we've used. And UTF-8 is actually the most ubiquitous string encoding. Different from a lot of other encodings, UTF-8 is a variable length encoding. What it means is a single character could take anywhere from 1 byte all the way to 4 bytes. I'm showing you some examples here. For example, the character A is 1 byte, the copyright symbol is 2 bytes, the Chinese character Xin is 3 bytes, and the pile Pu, which is a legitimate UTF-8 character, is 4 bytes. The reason UTF-8 became popular and the reason they is designed with the variable length encoding is it's great for memory. A lot of the data, as a matter of fact, probably most of the data, especially in the Western world, are just ASCII characters that would all fit in 1 byte. So when you're using UTF-8, you're only wasting 1 byte per string or per character. Whereas with a lot of other fixed length schema, you might have to use 2 bytes or 3 bytes always. But unfortunately, this variable length encoding, while it's great for memory saving because it's very compact, it's actually computationally very expensive. It just takes sort of the substring function as example. In the fixed length encoding, the substring function simply returns a number of bytes. If we know, for example, every character is 3 bytes, we'll just return the 3 times however many characters we want to return. But in the variable length encoding, we have to look at each of the character or each of the bytes 1 by 1 to determine what the character boundaries are. Sometimes some databases actually give the users the option of defining what your character set is, because often some users will only have ASCII character. But we feel that's not very realistic for 2 reasons. One is users don't often actually do that because they sometimes don't even know there's optimization they can do by themselves manually. The second is often data is actually maybe, say, vast majority of the data is ASCII, but then every once in a while, so one row comment that has a special symbol, and as a result, now you're going to corrupt your data if you don't declare properly the character set. The real question is, given the fact that most data, especially in the Western world, are just ASCII character set, but with the locations of UTF-8 beyond ASCII, can we get both the savings of UTF-8 in memory compactness and the performance of ASCII? Or put it differently, can we only pay for the performance penalty of UTF-8 when necessary, when we actually have that data? And we actually found a pretty interesting trick that we leverage in this case. And the idea is we'll actually separate any string processing into 2 steps. The first step is a fully SIMD ASCII detection algorithm that's run on the string. And this detection algorithm kernel is optimized so well, they leverage it's handwritten with AVX instructions. It can run at 60 gigabyte per second per core. So this is almost running at memory bandwidth. This is so fast that it's negligible overhead in virtually all cases. And the second step is depending on the result of the ASCII detection. If we realize a string is really just can fit in, the entirety of the string can fit in ASCII character set, we can run the special fixed length version of our string function. Otherwise, we run the variable length version. And with this technique, we achieve an order of magnitude speedup for most of our string functions compared with the original JVM variant, and in many cases, even compared with the SIMD version of the C++ variant, when the data are, for example, does fit in the ASCII character set. And this is done without the users having to manually do anything. It's just an automatic, auto-magic algorithm. For example, upper and substrings are significantly faster. But this is just one technique. I want to show you, there's one more example, which is regular expressions. It is used pretty frequently when people are dealing with or massaging data. It's very rare you will see regular expression showing up in the actual benchmark, but we have found the use of it in the wild so much they've spent a lot of time optimizing it. As a matter of fact, regular expression in Photon is more than 4 times faster than regular expressions elsewhere. Just to wrap up, Photon is a purpose-built execution engine for maximum performance that's built in C++. It leverages vectorization so we can take advantage of the data-level parallelism and instruction-level parallelism presented by modern CPUs. And it's also really designed to optimize for modern workloads in which there's a lot of strings everywhere. And I've shown you some examples of that. And to conclude, Delta Engine delivers best-in-class performance with all the expressiveness of Spark. It has 3 important components: a query optimizer, an execution engine, and a state-of-the-art caching layer. Both the query optimizer and the caching layer is available now on Databricks. And you can actually contact us to get access to the new execution engine that's called Photon. And thank you.